crap again. Hopefully they won't. All right, let's get this out of the way. Get you guys on your way. Yes. Crap. All right, now this is all going to be posted for you guys. I think I already posted it actually on Tuesdays.
This is going to be
just a synopsis. It's a synopsis of what you guys just discovered, okay, but in more concise form, rather than having you have to have an Excel spreadsheet out every single time you look at it. So synopsis, you don't have to write this down if you don't want to. I know a lot of you do, and that's totally fine. But you have the spread, you'll have the PowerPoint available to you, so you don't have to. Take this as, just like I said, it's an overview of everything you did on Tuesday and the first 30 minutes of today. Here's the whole point of why we just learned what we learned. You want to do this. You know it has that and that, but you're never going to know what they are. That's the whole problem with the population. They're too big to count. They're too big to count. You have to rely on estimates from the population. And how do you get the estimates? You draw samples. That's how you get your estimates. That's how the guy at the store told me that 90% of the identified girls are girls. Because somebody got an estimate somehow. Now, I don't know how scientific the estimate was. I don't know. But that was the estimate given to me. So you pull a sample. I'm going to call it size n. Size n. Little n for a sample size. And you'll get really, really comfortable with that in 244, those of you making that journey. Size n. We saw n equals 4, n equals 9, n equals 16, n equals 25, n equals 100 today. I mentioned n equals 10,000. 10,000 is a little bit excessive. Although a lot of Food and Drug Administration studies are done on 40,000, 50,000 trials. Because if you're going to put a drug out, you want to make sure there's no side effects or it does what it's supposed to do, better than placebo. So, please, Marnie.
So, just something you just said just sparked my curiosity.
Good.
So, if drug companies are actually taking a larger and larger sample size, wouldn't then that remove all those outliers and those side
not
effects?
all, but so
the
many.
Major ones,
oh,
like,
good. But the thing is, Marty, such a good question. If you take, I've made the claim in here a few times that if your sample gets large enough, essentially your margin of error shrinks to 0. Which is what you're saying, removing all the outliers. But the key word is essentially. Mathematically, it can never become 0. But you can sample a sample size large enough to show even a tiny difference is statistically significant. So for example, if you think that you have a new training method to have a kid ride his bike earlier than without this new training method, maybe the average age a kid rides a bike is at 3.5 years, and you can statistically prove that your method decreases it significantly. And you publish your findings because you did it on 150,000 children and your average was 3.45 years. That is statistically significantly lower if the margin of error is so small as to be imperceptibly small, mathematically and statistically. So yeah, you can't ever remove them all. You'll see why momentarily. Mathematically, you'll see why momentarily. Rylan already hit the nail on the head with what he said earlier. But you can't ever remove all of them, but you can shrink it down as far as you need it to be. Is that fair? Mm-hmm. Maybe. We'll see it symbolically here in a minute. Thank you. Great point. All right. First, you take your sample, find its average. If you do that across all possible samples, the average of all of those averages, I've made up a term called X double bar. I hope you forgive me for teaching you a new term, which you don't have to memorize, of course, on the last day of class. I didn't know how else to write it symbolically. X double bar. So if you average all of the averages, it is mathematically equal to mu. This is a real equal sign, FYI. That's not an approximately equal sign. That's a real equal sign. I didn't believe it. I've told you guys this story many times, how I said my stat professors must have hated me when I was in college, undergrad. Because I kept asking things like, why? How could you say that's equal? And that Excel spreadsheet, when I kept pressing F9, that average bar was never exactly equal to the population average. It kind of bumped around it, right? Sometimes it was above, sometimes it was below. And the professor would say things like, well, because it averages out. I'm like, exactly? Like, exactly averages out? Or approximately? No, exactly. Well, how? Well, and then, usually the class is over, I get to my office. So I went home and proved it. So if you want a proof, it's on the original page of your website. I know you don't. It's week 10. But if you're ever sitting in your research methods class in 2 years, or your U of O or OSU or PSU, and you're taking your 500 level research class, and they invoke the central limit theorem, you can go back to the original page, which will still be there, and you can look it up and see a proof for yourself. Here's the reality. That is mathematically true. It's also, unfortunately, practically useless. Well, here's why. This assumes you have all of the samples. How many samples do you get? Usually. You're a statistician or you're the FDA doing a study. How many samples do you get?
One.
One! You get one, and that's the problem. Your sample is not most likely equal to mu. What is it most likely? Say that again. David, thank you. It's most likely close to mu. Now define close. Close-ish. I define a 5-letter word with a 3-letter word, which is genius. Define close. Give me a little bit more than ish. I love the ish is huge. Actually, ish is a perfect way of describing close. Describe close using some phrases from this class. Okay, on average. So if we allow it to vary, on average, it's going to plop like this, right? It's going to go up and above and below.
I don't know, within one standard deviation.
That's what I was looking for. Within some measure of accepted variation. So what we do is we construct. This is the new term. Blame Ryland. It's his idea. It's his idea. This is a new term. For those of you in the research fields, you've already seen it. It's called the standard error. The standard error is like the sample standard deviation, except as your samples go up, your standard error has to go down. So what you do is, the standard error is actually your population standard deviation divided by the root of n, which is what you guys figured out about 20 minutes ago. Gorgeous. I can't prove that one to you without calculus, but that's on the original page 2 if you want to see it. You've got some really fun integration to do to figure this stuff out. But you guys noticed this. As your samples got bigger, shoot, your curves tightened up. That's the definition mathematically of curves tightening up. Because the variation is getting shrunk by a factor of the sample size. Yes. It's wonderful. All over 244. Every time you learn something new in 244, you're dividing by the square root of n. The students just take it for granted now. Where's the root of n? Oh, there it is. Because you have to. The larger your sample, the less... Think about it this way. The larger your sample, you're seeing more of the population, right? There should be less uncertainty in what you're measuring because you're seeing more of it. It's just this is how much more. So, Joe, we've defined close. That's a close. Now, here's where you have to put in your mind, this standard error, think of it like a standard deviation. But it's a standard deviation on that sampling distribution. So one of these contains 68% of your averages. 2 of these contains 95% of your averages. 3 of these are going to contain almost all of your averages. The same logic, this is why we got so excited earlier. I got excited, I don't know if you guys did or not. But when we said the bell curve was there, yay, we're like the bell curve? Because you got 2/3 of your data within one standard deviation. Your data here are the sample averages. Those averages, 2/3 of the averages are going to be within that of mu. 95% are going to be within that of mu. That's a gorgeous thing. And what happens to this as your sample goes up?
It goes down.
It shrinks, yeah? It shrinks, which means that 95% of your data might be from here to here with a small sample, but 95% of your data is going to be here to here on a larger sample, here to here on a larger... Marty, we're getting to answer your question right now. You can't ever get these to equal each other mathematically, because what would the value of that have to be if you wanted to make that equal to 0?
Zero.
Careful. If that's 0, that goes off to infinity. If you divide by 0, that's indeterminate, which means you go off to infinity. So in order to make that equal to 0, what would that have to be?
The whole population.
Mathematically, you have to be infinite, but the whole population would do it. Can I mention that real quick? Something about that, David, is a great point. If you measure the whole population, statistics is out the window. There's nothing statistical to talk about. You're talking about parameters. But in order to make that shrink to 0, mathematically, that has to be infinite. It kind of is like opposite of what Ryland just said. He said, in order to make this 0, make that 0. No, if that's 0, you're dividing a number by 0, which technically you can't do that. That's when things happen interestingly on graphs. But if you start making this bigger and bigger and bigger and bigger and bigger, this starts getting smaller and smaller and smaller and smaller. Bigger, smaller, bigger, smaller. Infinitely big, infinitely small, down to 0. No, but you can't do that. So that's, Marty, the mathematical reason why you can't make them go away. But you can shrink them down as far as you want them to be, based on your sample size. Is that a fair answer? Mm-hmm. Good, fair, good. Now, there's more mathematics behind it, of course, and it's buried on that page if you want to see it. But that's the big takeaway. You can get it as small as you want it to be, as long as you sample enough. But there are financial constraints to that, right? Maybe you can't destroy any more Lamborghinis because your factory is getting pissed off at you because you're destroying Lamborghinis. Yeah, Veronica!
Well, I just have a question about sigma in
Yes!
the numerator, because we're talking about
A sample, right? What I'm saying is mathematically, even though you don't know what this gives you a glimpse of it. Just like your sample average gives you a glimpse of your population average, your sample standard error gives you a glimpse of your population standard deviation. That's what I'm getting at. You don't have to know it. This is going to show up in your sample.
Okay.
This number is going to show up in your sample.
Yeah.
I'm going to back up a slide real quick, my friend. Just like this is going to show up in your sample.
Yes.
You're not going to see this. You're going to get a glimpse of that by seeing this, just like you're going to get a glimpse of this by seeing this. This is the icing on the cake. The fact that it goes down as your sample gets larger. That's like the game over. That's like, holy crap. That's when mathematics just gets gorgeous. Not only can you not see your sigma, but you can get a better estimate of your standard deviation. What? It's like having the cake and eating it too. For me anyway. You guys, it's 9:30 in the morning. All right. Now, don't vomit. Maybe too late. See if you understand what that means. I know you can. I know you can. This is kind of a 244-ish step. See if you understand what that means. Go ahead, read that, take it in. I know the answer is yes. Hold that thought, hold that thought. Listen. On average, mu will be within a usual range of values. I put usual in quotes to where we've used it here before. Let me see hands on this. Explain what the hell I'm talking about right there. And you can even insert other measures that I haven't included on here in Central. I'm sorry, Patty, you only bring your ear.
It means that the population average is going to fall within the sample average plus or minus 2 standard deviations.
Well, what percent of the time?
95%.
95% of the time. I didn't put 95 on there. But you don't have to have 95 on there because it's within 2 of them. You know that, yes? Yeah. Within 2 standard errors of your sample average, you're going to capture the average that you're looking for 95% of the time. You're going to miss it occasionally with the outliers, yes? But what's the definition of an outlier? By percentage? Something that happens
Less than 5%.
less than 5% of the time, which means you're going to miss them. You might get a deviant sample average, yes? You might get a deviant one, which means mu will be either higher than this interval or lower than this interval. But that's only going to happen 1 in 20 times on average. We have a whole lesson tied to that in 244. But this is the point. You do not know this. No, you don't. No, you don't. But you do know these from your sample, and you know that from your sample. It's the old joke, the old statistical joke. It's a terrible one. I think I may have told you before. 3 statisticians go bear hunting in the woods. Didn't tell you this one?
No.
First statistician jumps up, 5 feet to the left of the bear. Second statistician jumps up, 5 feet to the right of the bear. Third statistician jumps up and says, "We got him." That's this. That's this. First statistician, second statistician. You don't have to hit the number. You have to throw a net around the number and say it's somewhere in the net. That's all statistics is. Statistics cannot, when you read the news, we started the class with this. 60% of Americans favor offshore drilling in Alaska. No, they don't. 56 to 64%, somewhere in there said they favor. You can't take one part of the net and call this the part of the net that we believe. You have to believe the whole net. So you have to have a low and a high value. Now suppose your net is too wide. Suppose you are confident that 0 to 100% of Americans favor offshore drilling, and your boss says, "That's wonderful, I could have done that in my sleep with no math. Go get me a smaller net." What do?
Get a bigger sample.
You get a bigger sample, which is going to do what to these numbers right here?
Make them go down.
It's going to make them shrink, which means your net is going to go like this. So Marty, back to your awesome question, essentially you can make the net as small as you want it to be, but you can never make it down to a point. Because this guy always has a factor of that n in it. Does that make sense?
So you can manipulate the data?
It's not that. It's getting a, it's this. Check this out. Check this out. Let me come back to that. You get increased precision in your data. You get increased precision in your data. You're guaranteed accuracy. Remember we saw that the bell curves all centered on mu right away? That's accuracy. What you get better is you get better precision. It can seem like it's manipulating data. it would only be manipulating data if you knew where mu was. But you don't know where mu is. You're out there researching to find out where mu is. What you want to be able to do is target mu as precisely as possible. So I compare it to shooting a gun. Here are 4 targets. 4 of these targets, assuming that a marksman or a markswoman, marksperson, is trying to hit the bullseye in the middle. One of these targets shows high accuracy and high precision. One of them shows high accuracy and low precision. One of them shows low accuracy, high precision. And one of them shows low of both, low accuracy and low precision. I think I covered all the bases there. Pretty sure I did. All right. Who wants to grab one of them and tell me what it is? Grab one of those and tell me what it is. Accuracy versus precision. David McKenzie, go!
Well, precision would be like the lower right hand.
Okay, so how about this is high precision.
That's what I classify as.
And high accuracy. Why? First of all, why is it high precision?
Because precision is when they're clumped together.
Shoot! Tightly clustered, which means the net is smaller. So what you're calling shady statistics. I see why you're saying it that, Pat. The trick is that bullseye is not visible to us as statisticians. It's out there, and we're trying to find it. So it's more useful to have that as a measure of where the bullseye is than it is to have that as a measure. Both that and that, on average, are hitting the bullseye, yes?
Yeah.
But that one's hitting it more precisely. So larger samples will draw that down. Everybody buying high accuracy, high precision? High accuracy, low precision. You are guaranteed this by the central limit theorem. Because the central limit theorem promises, on average, you're catching the average. The question is, when your interval is between 7 and 12, and you need 0.10ths of accuracy, is it closer to 7 or closer to 12? We better go do another study and tighten it up a little bit and find out. It's not bad statistics, it's actually really, really good statistics. What you're saying is, we're trying to make the study agree with a commonly held belief. That is crappy statistics.
That's right.
I'm talking about exploratory, where we have no idea what this number is. Let's go try to discover it. I'd rather have that than this.
Well, yeah.
That's all I'm saying. What you're saying is correct, but that's not what I'm talking about here. This is exploratory statistics. I want to know what the effect this drug is, or what this drug has, on circulation. Let's go find out.
Okay.
It's not paid for by the drug manufacturer.
There you go. Thank
See,
you.
good. I'm not talking about bias that's built into the study. Some guy looking over my shoulder. I don't like that. Because that's when Harrison Ford has to run away from the guy that's trying to kill him.
The one-armed man.
The one-armed man, exactly. Go!
Well, the nice part about like the upper right hand is that since you are consistent in one area, you can adjust to move.
In a gun standpoint, right? So David's, this is high precision,
Low accuracy.
low accuracy. Exactly. Because you are clustered just like you are down here, but you're off target. So if you can recalibrate your machine to get you into target, then you're as good as this.
But wouldn't that also apply to like mathematical as well, where if you're clumped in one area, if you adjust your test?
Exactly. The trick is, you never have to worry about that with the central limit theorem, because you are going to be centered where you need to be centered. That's the best part. This would be an outlier situation, an extreme outlier situation with the central limit theorem. So good, you're right though. With the adjustment, you're just as good as you are bottom right. This I think you guys have already figured out. Low both. Everything's bad. Mathematically, the best part statistically is you are guaranteed one of these two. You're guaranteed to hit the target on average. You're just not guaranteed how tightly your cluster is without your sample size going up. That's, yes, good. Veronica?
But with that top right one, wouldn't you confuse the fact, since you don't really have the bullseye in the background and compare it to?
This is a great point! If you take the bullseye away, what's the difference between the top right and the bottom right? It's a great question. Who wants to field it?
One's more centered.
What? But the only reason we know it's centered out, I love what you just said. The only reason we know it's centered is because we see the bullseye there.
Well, you take the wider part, you still have a square, and it's in the middle of the square.
But what's a square? We can't see that.
Oh, okay, got
You
it.
see, all we see is data. Crap!
Is there a difference?
There is. This one's hitting the average, and that one's not.
But
So,
as you increase your sample size, you're going to naturally go closer to the average over time.
closer precise-wise, but you're guaranteed to be centered on the average from the beginning. Remember every single one of those bell curves. Hang on. Every single one, I closed them down, I apologize. Every single one of these bell curves you guys saw, you're going to see. Here we are. Every single one of these. is centered on the average already. You don't have to see it, it's showing it to you. The clustering becoming more tight is guaranteed as your sample size goes up. So it's a great question because it's a bit fictitious. Again, I'm showing you your population with the bullseye. But it's an afterthought because you're being shown where the bullseye is right here. Thank you for that question. Other questions on that? That was fantastic. Because Alan pointed it out, right? There's still a square there, but that square's fiction too. We're never going to see it. When you make a drug and you think it's going to work, you're going to run a test, you're going to see what happens. And assuming you did your study correctly and sampled correctly, the results of your sample are indicative of the results in the population. There's chances of error. We can measure those in 244, but honestly, it's showing you quite a bit of information right there in the sample. Freaking rad. And that's pretty much the whole takeaway. I mean, honestly, I don't know why I put homework on here, that's dumb. Pretty much, that's the whole thing. You don't even need huge samples. You don't even need huge samples. I want to tell you a bit of an artifact here. This number 30 has been used for years and years and years as a cutoff. You have to have at least 30. Have to have at least 30. So guess what Sean did in Stat 371 in 1994 at University of Delaware?
Use 10.
How come? Like, why? Why 30? Well, it's a universal standard. I'm like, I just built a Monte Carlo simulation that shows it happens with 4. So why is 30? It also works with 9, 16, 25. It works great with 100, but it worked well below. It actually works with like 2 and 3 even. Well, 30 is a uniform. Why? Guess what? Nobody seems to know why. But if you go to OSU, they're going to want you to know that number. I don't know why. They still want you to know that n equals 30 is kind of a cutoff. Even though you just saw that you could have it with much, much smaller than 30. The biggest thing, and far fewer can be fine, the biggest thing that you have to remember is your data has to be good. You have to have good, randomly selected data. That's the most important thing. Because the only way you're guaranteeing yourself a representative look at your population is by pulling good representative data. You don't want to do what Pat was insinuating, which is the intentional or unintentional bias by who's paying for your study, right? Who's paying for your study? Chocolate's great for your heart, paid for by the American Heart Association. Well, maybe. But is it also paid for by Cadbury? I don't know. That's what you have to go look at the data for. But mathematically, assuming you have a good random sample, so much in those 12 letters, yes? So much in those 12 letters. A good random sample. I want to study COCC students. I'm going to ask you guys a bunch of questions and take to the board of directors. Sound good? No, it sounds terrible! That's assuming you guys are a random sample of COCC students. That's crap! Why am I yelling so much? I don't know why I'm yelling anymore. You stop yelling. That's the big takeaway. That's 243 in a nutshell. All came right back to the beginning. I love the fact that this all comes right back to the beginning, which is what makes me happy about this course. How it ends up right back. Ask me that question, Brian, please. Ask me that question.
Oh, I was saying why not, because there's 30 of us, but we're not random.
Ha! That's the problem. The problem is mathematically we can do it, but that's the problem. It depends. Do I want to sample my 243 students? It's a slightly less biased sample of those, but it's not a good sample of those either because I got a class at 10:15. Maybe there's something inherently different about you guys. I want to take class at 8:15 versus I want to take class at 10:15. Some other variable I can't measure. What's that?
Because we're crazy like that.
Gluttons. Gluttons for punishment. Coming at 8:15. Not anymore, you won't. Except for next Thursday, I guess, yeah? I think that's it. And it's at 8.
Why?
8?
Why?
Well, it doesn't have to be. Want to make it 9?
No.
Yeah.
No. Well, hang on. Let's talk about it.
Let's get an average.
We're going to be talking about the class. You're going to be turning in your exam.
Okay.
And I have to build a survey. You guys, some of you have done the class evaluations.
Yes.
Thank you for doing that, by the way. I love that. That's institutional. They make us do that once a year. I do them every term, but I'm glad you guys did them for this term. I have more pointed questions I want to ask you guys about the way you learn. Because remember what we just talked about? The whole start of this class was about this project and how certain parts of it might have been confusing. I make adjustments in a lot of ways based on what I think, but a lot of ways what you guys think. You guys know how you learn, right? You know how you learn. I can't get inside your brains with COCC student evals. They're not designed. They do things like rate the instructor. It's like, what kind of question is that, rate the instructor? Or what grade do you expect to get in the class? I mean, you know that. You get a progress report every week. You know what you're going to get in the class. I want to ask things like, how frequently did you watch the quiz solutions on the YouTube videos? And did you find them helpful? I want to ask questions like, would it have been more beneficial to have the projects less uniformly spread out throughout the term? Would it have been more beneficial? These are the kind of questions I'm putting together right now. And you don't have to answer them right now, obviously. That's what Thursday is going to be. So I'm going to put them onto paper. And I'm thinking maybe 20 minutes, tops for you to go through them. Some open-ended responses, your opinions, and things like that. And then, if you guys want to stick around, we can like circle the wagons and chit-chat more. If you want. You can also just bail off at that point. I'll read the results later. So we don't have to start right at 8. Does anybody, would anybody want to start a little bit later than 8? Since class starts at 8:15, you want to just keep it at 8:15? You want to push it back to 9? What are you thinking? Not good.
People have finals too.
Yeah, final at 10.
Yeah.
Well, that's what I'm, oh, it's 10:15, I bet you. Yeah. Right, okay, so we shouldn't push it back too late, especially if the discussion gets going. Okay, how about, why don't we just keep it at 8:30? Is 8 too early? That's what I'm asking.
No.
8's okay?
Yeah.
Let's keep it at 8 then. Let's not let's keep it at 8. Let's keep it at 8. Okay. If you have to come up a little bit, yeah. Well, the thing is that there's no penalty for showing up a little late on that day. If you can't get here till 8:15, get here at 8:15. I'm just trying to organize if there's a circle the wagons discussion that wants to happen. I want to make sure everybody's there for it that wants to have it. You don't have to. You get the hell out of here in 20 minutes. Do the survey, get the hell out. Just get the hell here so you can get the hell out. Makes sense. Yeah, good. All right. Email me if you can stumble anything. We'll see you in a week otherwise. Yes?
Are you having office hours next week?
Crap, yes, and I have to put those on the web. It's written down. I haven't done it yet. I am putting office hours up for next week, I promise. They're probably going to be on Tuesday and Wednesday, because my Monday just vanished. So I'm thinking Tuesday and Wednesday is going to happen.